What's happening, class? This is Mr. Smith with reading quiz number 4 and a PowerPoint which shows you about the basics of continuity, which we talked about in a lab just a couple of classes ago. So, some basic definitions. Continuity. Our informal approach to continuity, which you saw in pre-calculus, and its faithful companion, which we'll see in the next reading, the intermediate value theorem, involve two statements. One, for functions that are continuous at an input, the intended output, or limit, equals the actual output. And a second statement, continuous functions on closed intervals take on every output in between the outputs of the endpoints of the interval. That's the IVT, which we'll talk about tomorrow. So, for continuity in particular, we need to formalize this definition. A function is continuous at x is equal to c if f of c is defined, limit as x goes to c of f of x exists, and limit as x goes to c of f of x equals f of c. These are three statements which you need to have memorized. And they can be collapsed down into a single statement that the limit as x goes to c of f of x equals f of c, assuming both the left and the right side parts of that expression exist. Another definition, a function is discontinuous at x is equal to c if it is not continuous. So how could it all go wrong for a function? How could it not be continuous? How could it be discontinuous? Well, we'll encounter three major types of discontinuities in this course. A removable or a point discontinuity, also called a hole in pre-calculus. In this case, the one-sided limits are the same but don't equal the function value. In symbolic notation, limit as x goes to a of f of x does not equal f of a. F of a may or may not even exist. The limit certainly does. So think f of x equals x squared minus x over x at x is equal to 0. Another type is the jump discontinuity. In this case, both one-side limits do exist, but they aren't equal. So formally, this means limit as x goes to a from the left of f of x does not equal limit as x goes to a from the right of f of x, even though both of those limits on either side exist. Think about f of x equal absolute value of x over x at x is equal to 0. Finally, we'll encounter infinite discontinuities, which could be either one-sided or a both-sided infinite limit. The classic example of that is f of x equals 1 over x at x is equal to 0. More details will be discussed in class about all this. Let's look at some practical considerations. To find the points of discontinuity of a function, we think about our basic definition of continuity. Three possibilities are evident. Either the limit does not exist, the function does not exist, or the two don't match. Functions are usually only discontinuous at what we'll call suspicious points. Basically breaks in a piecewise function, or if you've got some sort of a rational function where you might have a division by 0, or any other domain errors may cause a point of discontinuity. When dealing with piecewise functions, as we'll see in the next example, we want to investigate each of the parts first, and then look to see whether or not there are any breaks in the function. Do the pieces match at each of the breaking points in the domain? So let's look at that example. Where is f of x equal x cubed minus 2 when x is less than negative 1, 2x plus 7 when x is between negative 1 and 3, including negative 1, and x squared plus 4 when x is bigger than 3, continuous. So if you'll notice, each of the three parts is a polynomial. And as we talked about in class, polynomials are continuous everywhere. The piecewise function, therefore, will only be discontinuous at points where it would break. And that's only a possibility. Those are at x is equal to negative 1 and x is equal to 3. So let's consider those 2 points. At x is equal to negative 1, limit as x goes to negative 1 from the left is negative 3. And we get that by plugging in negative 1 into x cubed minus 2. The limit as x goes to negative 1 from the right is 5. We get that by plugging in negative 1 into 2x plus 7. And the function value at negative 1 is also 5 because we have the less than or equal to statement in our piecewise function. At x is equal to 3, from the left of 3, we get a limit of 13 from the left. From the right, when we plug in 3 into the x squared plus 4 portion, we get a limit of 13 as well. However, you notice that f of 3 is not defined. There is no piece that includes x is equal to 3 as part of its domain. Since for negative 1, the limit as x goes to negative 1 to the left of f of x does not equal the limit as x goes to negative 1 from the right of f of x, f is not continuous at x is equal to negative 1. It's what's called a jump discontinuity. The limits on either side exist, but they don't match. Even though limit as x goes to 3 from the left of f of x equals limit as x goes to 3 from the right of f of x of 3 is not defined, so f is not continuous. The limits match on either side, but we're missing the function value. We call that a removable discontinuity. Can we make a function continuous? All we need to make a function continuous at a certain point is to make sure that the left and right side limits match at that point, and that the limit matches the function value. And oftentimes we'll be working with functions where we've got a mysterious coefficient that we need to find out, and finding out that coefficient will tell us whether our function is continuous. So, for what value of the constant c is the function f below always continuous? F of x equals cx squared plus 2x when x is less than 2, and x cubed minus cx when x is greater than or equal to 2. Our objective. The function is almost always continuous because it is a polynomial, but we do have a concern at x is equal to 2, which is the breaking point of our domain. So we need to make limit as x goes to 2 of f of x equal to f of 2, which, taking it a step backwards, means we need to make limit as x goes to 2 from the right of f of x equal to limit as x goes to 2 from the left of f of x. Well, the left side limit is 4c plus 4. That's what we get when we plug in x equal to 2 into the top portion of our piecewise function. The right side limit is equal to 8 minus 2c. Similarly, we're plugging in 2 to the bottom part of our piecewise function. And we need those two left and right side limits to be equal in order for our function to be continuous and our limit to exist. So we set 4c plus 4 equal to 8 minus 2c. Solving, we get c is equal to 2/3. We also notice that f of 2 is equal to 2 cubed minus 2/3 times 2, which is 20/3. And this is what we get when we plug in our c value into both of our limit statements. Other suspicious points beyond piecewise breaks. Question: find the points of discontinuity of the following function and state the type of discontinuity. For example, g of z is equal to z minus 3 over quantity z squared minus z minus 6. Notice that if we factor the denominator, we get a z minus 3 over z plus 2, and therefore we get two suspicious points at z equal to 3 and z equal to negative 2. When you investigate the limit, as you go to the right of negative 2, limit as z goes to negative 2 from the right of g of z, we get positive infinity. If you'll remember, we talked about all that in reading quiz number 2. Therefore, we have an infinite discontinuity at z is equal to negative 2. At z is equal to 3, you'll notice that the factors cancel. Because they cancel, we get a limit to exist, a numerical limit. And if you evaluate it, that limit is 1/5. G of 3, however, does not exist. So, the limit exists, the function does not, therefore we have a removable discontinuity at z is equal to 3, also known as a hole. Find the points of discontinuity of the next function and state the type of discontinuity. Here's a little more complicated one. R of x is equal to x cubed plus 3x over absolute value of x times x minus 2. We have two suspicious points, x is equal to 0 and x is equal to 2. Notice that the limit as x goes to 2 from the right of r of x is equal to infinity. We get that by plugging in. So there is an infinite discontinuity at x is equal to 2. However, at x is equal to 0, we notice that we can factor our top to be x times x plus 3. It doesn't quite cancel out with the bottom, which is still the absolute value of x times x minus 2. As x goes to 0 from the right, however, the absolute value takes on positive x. And when we cancel out x's and evaluate the limit, we get a negative 3/2. On the left side of 0, however, absolute value of x is equal to negative x. So when we replace our absolute value with negative x, we get a limit of positive 3/2. Therefore, we have a jump discontinuity at x is equal to 0, since the one-sided limits both exist, but they do not match.